Okay, so today I'm going to do a review for the final. This is not a comprehensive review, but it's just some of the questions that my students asked me to cover are the most frequently requested topics. So I'm going to start with this one. And the first question I always ask myself is this an acid-base reaction? If it's not an acid-base reaction question, then I ask myself, I'll just write these down. Substitution, elimination. If it's not one of those, then is it an addition reaction, something we learned in chapter 8? If not, then is it a reaction of alcohols or ethers? That's something we learned in chapter 11. And then is it a radical reaction? What we learned in chapter 10. So those are the big things you have to ask yourself. So this is not an acid-base reaction. Substitution or elimination, it's a good candidate for that because there's a nucleophile and a leaving group. So if I'm saying this is probably a substitution or elimination question, then I have to ask, which one is it? Is it SN1, SN2, E1, or E2? And I've done a lot of videos about how I kind of determine, but first I look at the nucleophile. If it's negative, that means it's a strong nucleophile. If it's neutral, that's a weak. So if it's strong, if it's negative, then it favors 2. If it's weak, then it favors 1. If it is strong and it favors 2, then we know that a primary leaving group or substrate is going to favor SN2 because that's a substitution reaction. And a tertiary leaving group is going to favor E2. Also, heat favors E2 and a bulky nucleophile. Same sort of thing with SN1 and E1 because they have the same first step. They start with the leaving group leaving. You get that carbocation. Then that one's actually, I think, kind of harder to tell. So you could use heat or a bulky nucleophile is going to favor E1, but those are harder, I think, to tell apart. I have a more extensive video on this if you want to check it out, but just really quickly, if we look here at the NaOCH3, so this is basically if you have an Na, it's the same thing as OCH3 minus. So that's negative, so that's strong. So it's going to favor the 2s. It's a secondary leaving group, so it could go either way, SN2 or E2. But the heat makes me think that this is an E2. When you have an E2, you have to consider stereochemistry. You have to consider that for all of them, but specifically E2 is anti-periplanar or anti-coplanar. And you also have to check if it's Zaitsev or Hoffman. So in this case, ask yourself, is this Zaitsev or Hoffman? It'll favor Hoffman if it's bulkier. It'll favor Zaitsev if it's more small, narrow. That means it can get into the smaller spaces more easily, and it can form the more substituted alkene, which is also the more stable. So this is going to be Zaitsev. So now we have to make sure that it's anti-periplanar. And I forgot to draw in, I actually drew this in for my students. If it doesn't have stereochemistry, then you don't have to worry about this. But if it does have stereochemistry, you need to make sure. So if I drew this Newman projection, the bromine's coming towards me. There's an implied hydrogen going away. So if I'm looking at it from this angle, the bromine would be on my right and the hydrogen would be on the left. So I looked at it from this angle. So here's a bromine and a hydrogen, and then going straight up is a CH2CH3. And then the back carbon here is going to have, if this bromine pointing out was on the right, then this CH3 pointing in must be on the left. So then there's a implied hydrogen that's a wedge that's coming out also on the right, and then CH2CH3. So these bromine and hydrogen are not anticoplanar, so we need to rotate. And I'm just going to leave the front carbon the same, and the back carbon is going to be I moved all of them over 1. So these two are opposite each other. So that right there is going to be where my double bond forms. So we have 2 ethyl groups on the top and an H and a CH3 on the bottom. One of my students asked me why it's not drawn like this. And it can be drawn like that. I just draw it like this because it makes more sense. If you had the methyl group on top and the ethyl group on the bottom, that would be a different configuration. So this is a way to check yourself on another topic, and that's E versus Z nomenclature. So let's ask ourselves if this is E or Z. So on the left side, if this is a carbon and this is a hydrogen, this is going to be higher priority because if you're looking just at the point of attachment, you just look at that atom. So one carbon, one hydrogen. The carbon is going to be heavier, so it's a higher priority. Over here we have two carbons, so then you have to look at the next point of attachment. So carbon, two hydrogens, carbon with three hydrogens. The extra carbon up here makes this higher priority because this carbon is attached to a carbon and two hydrogens. This carbon is only attached to three hydrogens. So this is Z configuration. If we drew like this, the higher priority would be on opposite sides of the double bond. I'd cover up the double bond if I'm not sure. And so that would be E configuration. So now we've covered, can you tell SN1, SN2, E1, E2, E2 anti-coplanar, and EZ nomenclature all in one question. So now let's look at this one. We're going to ask ourselves the same question. Is this acid base? This could be a base, but I don't see a good acid available. Is it substitution or elimination? Well, there's a good leaving group, so I'm going to say could be substitution or elimination. And then I'm going to ask myself, is this a strong or weak nucleophile? Well, O- is a strong nucleophile, so it's going to favor 2. The leaving group is secondary, so that doesn't really give us any hints, but the nucleophile is bulky. So the bulky nucleophile makes me think it's going to favor E2. We don't have to worry about if it's anti-periplanar or not because no stereochemistry was given. But we do have to ask ourselves, is it Zaitsev or Hoffman? And because it's bigger and bulkier, it's going to favor Hoffman. So that the nucleophile would come in and take this proton here. Those electrons that made up this bond will form a double bond there, and the bromine will leave all in one step, and it happens all at once because it is an E2 reaction. And then you have a double bond that's formed right here. So you can see the difference if you use a bulky nucleophile, your double bond goes here in between carbon 2 and 3, but if you do it up here, it goes between carbon 3 and 4. Okay, and now next question, question 3, same thing. Do we have an acid base? No, I don't see a good acid or a good base. Maybe OCH3 minus could be a good base, but there's no proton that's readily available. Substitution or elimination, well, again, there's a good leaving group, and this OCH3 minus is a good nucleophile. So I'm going to say this is substitution or elimination, and then I go back to my chart. This is negative, so it's a strong nucleophile, so it's going to favor 2. It could be either SN2 or E2, but because there's heat, I think it's going to favor E2. So if there's E2, there's two things we have to check. Is it anti-periplanar or is it Zaitsev versus Hoffman? Anti-periplanar, we do need to check that. Zaitsev versus Hoffman. This is a smaller nucleophile, so it's going to favor Zaitsev, so it's going to try to form the more stable. But let's make sure we can get an anti-periplanar there because if you have it in a ring, it can't just rotate. Here, this was around a single bond. We could rotate to make sure the bromine and hydrogen were opposite of each other, but you can't do that with cyclohexane. So when I'm trying to convert cyclohexane to a chair, my first wedge is going to be axial, and my second wedge is going to be equatorial. And I have a whole video on that if you don't remember why it's that way. But that means that this dash will be axial. So if I'm drawing my chair, I'm going to make my bromine axial, and then my methyl group is also axial based on this chart that I drew over here. Well, that's a problem because if you want to get a good leaving group, or a good E2 reaction, they need to be anti each other, right? So this bromine's pointing straight up. A hydrogen needs to be pointing straight down on an adjacent carbon. There is not a hydrogen pointing straight down there. There's a hydrogen in the equatorial position, and we can't rotate this ring to make the hydrogen go into the axial position without changing the bromine. So instead, we're going to look over here. There's a hydrogen in both the axial and the equatorial position. So actually, this carbon between carbon 1 and 6 is going to be where the double bond is favored to go, because there's not a hydrogen that's available for an E2 reaction on carbon 2. So presumably whichever one of these hydrogens is a wedge, that one's going to be stolen. And then the electrons that made up this bond will stay behind to make a double bond, and the leaving group will leave. And your answer would be this. Okay, so that covers how to convert from from a flat cyclohexane ring to a chair, and that also covers E2 anti-coplanar reactions and telling the difference between SN2 and E2. Now the next question, again, I'm going to go up to my list at the top. Is this an acid-base reaction? No, I don't see a readily available base or acid, and we're just looking at part 1 for the first part. Is it a substitution or elimination reaction? There is a good leaving group, but not a good nucleophile here at the top part. So then is this an addition reaction? Ding, ding, ding. I see this H2. I see this double bond. I know that H2 is going to get rid of a double bond whenever it is with nickel, platinum, palladium, carbon. So that's going to end up with I just think of it as deleting the double bond. I mean, it just gets rid of that second bond by adding 2 hydrogens. That's known as a hydrogenation. You can take an alkyne all the way to a single bond also with H2 and nickel or platinum or palladium, or you can use a poisoned catalyst to stop at the alkene. That's Lindlar's catalyst, dissolving metal reduction, or I think it's palladium on carbon with calcium carbonate and quinoline, something like that. So these two, Lindlar's and this one, both are cis. Dissolving metal reduction makes trans. So hopefully you remember that. So these add syn and this one adds anti. Then the next step is ethanol and heat. So I'm going to go back to the top. Is this acid base? Well, there's not really available proton or a good base. Substitution or elimination? Well, we do have bromine and we have a nucleophile of some kind. So I'm going to say yes, this is a substitution or elimination question. So let's go back to our chart. Is this a strong nucleophile or weak nucleophile? Well, ethanol is not negative, it's neutral, so it's weak. And then it has heat, so I'm assuming it's going to be an E1 reaction. So the first step in an E1 reaction is the leaving group leaving a carbocation, and whenever there's carbocation, you always have to look for rearrangement, and that will occur in this situation because there's a methyl that can shift over to fill in that carbocation, leaving a tertiary carbocation, which is more stable. And then the ethanol will come in and attack. Oh, wait, no, this is an elimination reaction because there's heat. So actually, the ethanol will come and take this hydrogen, and it'll fill in that leaving group. And I don't have any stereochemistry drawn, so you don't have to worry about it. Let's see. So it'll either give you this or it'll give you the opposite, the Z. You could get this or you can get this. If there's a multiple choice question, only one right answer would be there. Okay, so now what are the 4 ways to turn alcohol into a good leaving group? So the 4 ways to turn alcohol into a good leaving group. Hopefully you remember, hopefully you can pause this and ask yourself that question, but one of them is protonation. Another, and that protonation just basically turns it into water, which is a good leaving group. So if you have an alcohol plus H plus, it'll say OH2 plus. Another is SOCl2. That's basically an SN2 reaction to turn primary and secondary alcohols into chlorines. Another is PBr3. It's helpful if you know the mechanism for this. I'll draw it over here, but that basically just turns alcohols into bromines. It only works for primary and secondary because it is an SN2 reaction. SN2 reactions don't work on tertiary carbons. And that also means that there's an inversion of stereochemistry. So if you have OH as a wedge, it turns into a dash, or if you have it as a dash, it turns into a wedge. For both of these, you get inversion. And then the last one is tosylates and mesylates. If you have OH and then you have tosyl chloride, it'll turn this into OTS, and it actually inverts stereochemistry, so it'll go from a dash to a wedge. Similarly, if you have MsCl, it would turn this into OMS, and that's just a good leaving group. Oh, wait, it retains stereochemistry. I'm sorry, I said that wrong. So these invert stereochemistry, these retain stereochemistry. So if it starts as a wedge, it ends as a wedge. If it starts as a wedge, it ends as a wedge. There's another one that sometimes gets thrown around as being a way to turn alcohol into a good leaving group, and that's alcohol with HBr. But the first step in this is a protonation step to make OH2. So like you already turned it into a good leaving group, and then it leaves and the Br attacks. But you could get rearranged with that. So I don't love that one. I don't use it a lot. But these four, these come up a lot. You should definitely know these. Now let's go ahead and solve this question, which starts with turning our alcohol into a good leaving group. So use PBr3. And the first step is this alcohol comes and attacks and kicks out a bromine. So this is the first step in the mechanism. You don't have to have this memorized, but it's helpful to know. PBr2 and then Br minus will come in and kick this out. I guess you should have it memorized, but you don't have to draw it out every time. So that's how you get your SN2 reaction where your bromine is a wedge. So you have your bromine and your methyl group there. And then you have NaI. So NaI, is this going to be an acid-base reaction? NaI with this? I don't think so. I don't see an acid-base. Could it be a substitution or elimination? I would say yes, because there's a good leaving group and I minus can act as a nucleophile. I minus is going to be negative, so it'll be a stronger nucleophile. So I think this is going to go as an SN2 reaction. However, I will say because this is kind of bulky, it'll probably have some competing E2 reaction. So this I minus is going to come in and kick out your bromine. And it's going to proceed with an inversion of stereochemistry because it's an SN2 reaction. And then you have this methyl. And then the next step looks actually like another substitution or elimination. It doesn't look like an acid base. There's a good leaving group. And then there's a good base. There's a good leaving group. Looks like a substitution or elimination. It's a strong nucleophile, so it's because it's negative there. And there's no heat. So I think this would proceed as an SN2 reaction. So the ETO minus would come in and kick this out. I think I was intending this to be another another elimination reaction, and I just forgot to actually draw that. So if this was an elimination reaction, and we had the I minus as the leaving group, we would need E2 to be anti-coplanar. So this I is axial, this CH3 is axial, so it would form as above. You would get this as your product. But if you did it on the an E2 reaction on this, the more stable product would be right here because you would have an anti-coplanar hydrogen there. Maybe that was a little confusing. I just want you guys to be thinking about all the different aspects of each question. So the main one is right here. If you did this and then a substitution, we basically just did 1, 2, 3 substitution reactions in a row. Not a lot of point to that except to help you remember how to identify when you see substitution or elimination questions. Okay, now we have the same type of question except with tosyl, and the big thing here is for you to see that if you have alcohol and then you use, actually this is a mesyl, CH3SO2Cl, that's going to proceed without inversion of stereochemistry, and then if you had NaI again, it would come in and attack. And so you'd have I minus, or I as the dash, and CH3 as the dash. And if we had heat here on this question, it would be an E2 because it's the exact same one as last time. So I'm going to draw this out. If we have a wedge as an axial, the next wedge would also be axial, or would be equatorial, I'm sorry. And then the dash here, where the implied hydrogen would be axial. So we'd have our I minus like this, and your CH3 would be equatorial, and your hydrogen would be axial. So there is an anticoplanar hydrogen available right here. So if this had heat, this could come and attack your anticoplanar hydrogen, and the electrons would fill in, and this kick out, and you would get this as your product. So I'm sorry if that was confusing. I meant to put heat on both of these so you could see that if you start with an inversion of stereochemistry, it can change your overall reaction. That's kind of what I was just trying to show you. But if you can follow with what each one of these does, you're in good shape. Okay, the next one, is this an acid-base reaction? I'm going to say not because there's not a clear acid or base. Is this a substitution or elimination question? Well, there's a good leaving group, and there's a good nucleophile, or a good enough nucleophile. So that nucleophile is neutral. It's not negative, so I'm going to say it's weak. So this is going to favor 1. Tertiary is going to be equally favored for both. It's not heat, it's not bulky, so I'm going to say this is going to be predominantly SN1, although E1 always does come into play as well when SN1 occurs because their first step is the same. So the first step is the leaving group leaves, forming a carbocation, and then your CH3OH will come in and attack, and you get a protonated OCH3. That protonated will be deprotonated either by the alcohol or something else. I usually just put minus H+. And there's your final answer for your substitution reaction. Okay, again, let's see. We have OCH3 minus and methanol as your solvent. So this isn't an acid base. It's got a good leaving group and a good nucleophile, so that makes me think it's going to be a substitution or elimination. It's negative, so it's strong, but we don't have a tertiary leaving group. We don't have heat or bulky nucleophile, so I think this would favor SN2. So that's different than some of the other ones. So when we have a good nucleophile for an SN2 reaction, it does the backside attack. Make sure you know the mechanisms for each of these so you know why it does stuff like this. It does the backside attack, and you get OCH3. So if I had drawn my stereochemistry there, if we knew the stereochemistry, it would be inversion of stereochemistry. And because it's already OCH3 minus, there's no need to deprotonate, so this is the whole reaction. And that's your final answer. So these are very similar. This is what you'd get for an SN1, and this is what you'd get for an SN2. So make sure you know the rate of an SN2, SN1, E1, and E2. The rate of an SN2 is dependent on both the nucleophile and the substrate. It also has the rate constant there because, here, let me see if I can't zoom in a little. Because it all happens in one step, right? The nucleophile attacks as the leaving group leaves, so the speed of the reaction depends on how much you have of both of those. Whereas in SN1, the first step is the leaving group leaves, so the rate is only dependent on the substrate where the leaving group is. Same thing with E1, the leaving group leaves first, so the rate is only dependent on the substrate. And then for E2, it's the same thing as SN2, where the nucleophile attacks at the same time the leaving group leaves, so the substrate and the nucleophile are both involved. So what happens if you double the solvent? Double the solvent, halves the concentration. So it would cut the speed of these in half, and it would cut the speed of these by a fourth. What happens if you double the concentration? Well, if you double the concentration of both, this would quadruple, this would double in speed. If you multiply this side by 2, you have to multiply this side by 2 also. Okay, question 11. If you have alcohol and H2SO4, this is an acid-catalyzed dehydration. I usually, if I see H2SO4, I rewrite it as H plus and H2O because it's easier for me. And how do I know this is an acid-catalyzed dehydration? Well, it's not an acid-base question because there's an acid, but there's not a good base. So it must be a substitution or elimination question, but there's not a good nucleophile. Well, actually, if you redraw it as H plus and H2O, water is a good nucleophile, but OH isn't a good leaving group. But if you protonate OH, it becomes a good leaving group. So you can do the first step is an acid-base reaction to make this. OH2 plus is, OH is enough of a base, H plus is enough of an acid to protonate. And then what do we still have? We have water, which is a good nucleophile, and water, which is a good leaving group. So this leaving group will leave. It's acid-catalyzed dehydration is a special kind of E1, and I made a TikTok video about that, and we talked about it a lot in chapter 7. Leaving group will leave, and then the water in solution, will come and take this hydrogen. Sorry, it's dehydration. So the water will come and take this hydrogen. Nope, I made a mistake. Did you guys see the mistake I made? Hopefully you got it. The leaving group will leave. It makes a carbocation, and that can undergo carbocation rearrangement. You always have to check for rearrangement when there's a carbocation. So the carbocation will form there, and then the water can steal either one of these protons. It's identical, so it doesn't matter. And you'll end up with, did I draw too many? This as your final product. Because the proton is stolen from here, the electrons fill into where that carbocation is. So I almost missed that question because of carbocation rearrangement, so always check on it. Now take this alkene from question 11, so the one we just created, and undergo acid-catalyzed hydration, hydroboration, oxidation, and oxymercuration demercuration. So all these are different. Acid-catalyzed hydration is actually kind of just the opposite of what we just did. So if you did H plus H2O, that's acid-catalyzed hydration. The first thing that happens is this will get a hydrogen attached to it, and the carbocation will form at the most stable position. And then the OH2 will come in and attack, and you'll get OH2 plus, and then that deprotonates to form addition of an alcohol. Oh no, I ran off screen. Sorry, there you go. So this adds Markovnikov, and you get a racemic mixture. This doesn't matter because it's symmetrical, but if you did, you would get a racemic mixture. But you also have to look out for rearrangement. Now, if we did the same alkene, I think it was this structure, with hydroboration oxidation, that's HgOAc2, THF, and water. And that adds Markovnikov with no rearrangement, but actually doesn't matter about rearrangement now because it didn't actually rearrange. The carbocation formed, but it was already the most stable. So you'd actually get the same product because it's also adding Markovnikov with no rearrangement. This initially adds anti, but when you do the hydration step in the second part, NaBH4 and NaOH, it scrambles it. So you'll get a mixture of stereochemistry. And then if we do hydroboration oxidation, that's BH3THF, H2O2 and NaOH, and that adds anti-Markovnikov. So the alcohol would add down here. And if you want to see the mechanisms for all of these, you are more than welcome to check that out. I have a video where I go through all the main ways to add water across a double bond. So take that and undergo acid-catalyzed hydration, hydroboration oxidation, and oxymercuration demercuration. We did that. The regiochemistry for each of these, Markovnikov, Markovnikov, and anti-Markovnikov. And then the stereochemistry is a racemic mixture. This is a mixture as well, and it adds syn and anti-Markovnikov for the regiochemistry. So we did the regiochemistry and the stereochemistry. Okay, the next question is draw all resonance structures for the benzylic carbocation below. What does resonance do to that positive charge? Okay, so this is a positive charge. There's an absence of electrons. So whenever there's an absence of electrons, I'm trying to fill that absence of electrons in. So I think these electrons would move over and leave a gap behind where they were previously. And that should be a valid resonance structure because you could only have 2 hydrogens here if it was positively charged. You wouldn't have 3. So now with 2 hydrogens, this is fully satisfied. But this one formerly had 1, 2, 3, 4 things bonded to it, and now it only has 1, 2, still has its hydrogen, so 3. So this is a proper resonance structure. And then we're just going to see if we can't do that again. So that should be fine because there's 1 hydrogen bonded here. There still is. There is always 1 hydrogen bonded here. Down here, we're missing a hydrogen, or we're missing the double bond, so it becomes a carbocation. And then we can just fill in 1 more time. So always check to make sure it's a valid resonance structure and that you have gone through every step to add, like just move your electron one thing over. Don't try to go all the way around in one step. Just look, can I move one thing? And that's a legitimate option. Now, you might ask, could I move my could I move my lone pair right here? You could, but that doesn't really do anything to the positive charge, which is what you're trying to fill in. So I would pay special attention to that. So what does the resonance do to that positive charge? Well, the resonance delocalizes the positive charge all the way around the ring. So instead of just having a positive charge concentrated here, it's concentrated here, 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 and here. So you have a partial positive actually on this hydrogen, or on this carbon, and this carbon, as well as this carbon, instead of it all being focused in one place. If you had a benzylic carbanion, you have to think of it differently. You have excess electrons right here, right? So you probably have 2 hydrogens and a lone pair to give it that negative charge. So where can you put this? If you made your lone pair into a bond right here, that would be fine, except then you'd have 1, 2, 3. There's, this bond right here is also, my benzene's not very good. So 1, 2, 3, 4 bonds to carbon. So you can't have that many bonds to carbon. So you can break this double bond and make a lone pair to make up for it. So anytime you form a bond, you have to make sure that it's filling in an absence of electrons, or you're going to have to break something else. So, I redrew that same structure. So now we've broken this bond to make lone pairs. These other 2 are still fine. So that allows us just to move the negative charge, and we don't have any carbons with too many bonds to them. So now I'm going to do the same thing. I'm going to try to add that lone pair as a bond right here. Well, there's already an implied hydrogen, so we have 1, 2, 3, 4 bonds, so that's too many, but I can break this and make it a lone pair again. So and then we can do that again. This can go here, this can break. And so now we've made it to where the lone pair is delocalized all around this ring. And so the concentration of that lone pair is less affected. You could do the same thing with a radical all the way around the ring, and it stabilizes it as well. That's why benzene rings are good to stabilize. And that's a quick review of how to do resonance. But I highly encourage you to do resonance questions. There will be at least one on your exam. Okay, next, what's the pK for each of the following? Okay, alcohols are 16 to 18. Carboxylic acids are 4 to 5. Alkynes are 25-ish. Alkenes are 45-ish. And alkanes are 50-ish. So that's the pK for each of those. Make sure you check those out. And then I also have a video on TikTok where I do flashcards for my for pKa's. Okay, so next question, what is the strongest acid? So I always get this mixed up, strongest acid, highest pKa, whatever. So it's going to be the smallest pKa is the strongest pKa is the strongest acid. So the smallest pKa is this one. So that's going to be the strongest acid. And which has the weakest conjugate base? Okay, so stronger acid, weaker base. They're inversely related. So if this is the strongest conjugate acid, that means it's most willing to lose its proton, and it's willing to lose its proton because whatever is left behind is going to be stabilized. So it's not going to be too reactive. So this is the strongest acid, so this conjugate base is the weakest, so it's also actually B. Which one has the strongest conjugate base? Strongest weaker acid would be stronger conjugate base. So then you have to ask yourself, which is the weakest acid? This one, weakest, because it's the largest pKa. So if that's the weakest acid, that means if you had a CH2, CH3 carbanion going around here, if it lost its proton, that would be very reactive. It would be trying to react quickly. So that's just a reminder of how to tell that. So this would be the strongest conjugate base, and this would be the weakest acid. Okay, now which identify, I think I just meant to say identify the acid and conjugate acid. Okay, well, typically if something's negatively charged, that's going to be your base. And if you have a positive counterion, then that's negatively charged. But also you can look at the transformation. So this benzene went from being OH to being O minus. So that tells me that this is the acid. And if this is the acid, this is the conjugate base. If this is then the base, this would be the conjugate acid. So there's the acid and there's the conjugate acid. Next step is, what is the pKa for each acid? So phenols, you might be tempted to put this in alcohol, 16 to 18, but this is a special type of alcohol. It has that resonance that we talked about on question 13. It actually has a pKa of 9 to 10, actually. It's in the 9 to 10 range. So that's the pKa for that acid. For the conjugate acid, this is an alcohol, so it's 16 to 18. Sorry, 16 to 18 for alcohols. So which side of the reaction is favored? Well, weaker acids are favored. Weaker acids, I don't know why I wrote that in cursive, just came out. Weaker acids are favored. So this is a stronger acid because it's a smaller pKa. This is a weaker acid because it's a larger pKa. So this side of the reaction is favored. So this arrow drawn is correct. Usually it's like actually in an equilibrium, but the equilibrium favors this side. So these are more likely to form as products. Okay, question 16, which is the strongest acid and why? Okay, so this is a question about the inductive effect. So basically all of these have the same functional group, so you can't just estimate what the pK of the functional group is. You have to look at something else, and these have some kind of electronegative atom attached to them. Let's see, this one is 1, 2, 3. 1, 2, 3 away. So the chain's a little bit longer, but all these chains are the same length. And when you have something like this, what you have to look for is actually going to be the most electronegative, and it's going to be the closest to the atom. And this is, again, acids are all about the thing that's most acidic is going to be the thing that's most willing to give up its electron or its proton, because the negative charge that's left behind can be stabilized. And if you have this negative charge, that's going to be, because of resonance, focused here and here. You'll have a partial negative there and a partial negative there. But if you have this with a fluorine, actually, let's make it 3 fluorines. These fluorines are all really electronegative. So you'll have a partial negative here and a partial negative here due to resonance, but you'll also have the inductive effect pulling those electrons towards it. So you're going to get partial negatives on all of these fluorines as well. which means that negative charge is dispersed all around your molecule and not just onto oxygens. So this is going to be more willing to give up a proton because the oxygen charge that's left behind is going to be more stable, if that makes sense. So anytime you have a more inductive atom closer to your functional group, it's going to be more willing to give up a proton. Fluorine is the most electronegative atom, and in this one, the fluorine is 1 carbon away. So the only way we can get better than that is if we have 2 fluorines. This has a bromine, so that's not going to be as good as fluorine. This has a chlorine, not as good as fluorine. This has another fluorine, but this fluorine is closer. So this fluorine is, we have a fluorine right here, and we have a fluorine right here. So the one where the fluorine's closer is better, so we're going to get rid of that. And this has an iodine, so not even close. So A is going to be our strongest acid because it has the most electronegative atom closest to the point of the hydrogen. Okay, make an isomer flowchart. So this is just to remind you of what types of isomers there are. There's 2 main types of isomers. There's constitutional isomers and stereoisomers. Constitutional isomers, I like to say they have different condensed formulas. So these are the same number of carbons and hydrogens. They're both C5H12. Their condensed formula would be CH3, CH2, 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 CH3. Sorry, I know this is small. I have limited space. For this one, the condensed formula for this one would be CH3, 4. So they have the same number of carbons, hydrogens, atoms, but they have different condensed formulas is what I like to say. Stereoisomers would have the same condensed formulas, and there's 2 kinds. There's enantiomers and diastereomers. And enantiomers are non-superimposable mirror images. So that's if there's like a left and right hand and you can't put them over top of each other. To do that, you have to flip it over, but then it's not actually exactly the same. So those are stereoisomers, or those are enantiomers. Right and left-handed is what I call them, right and left. And they have R and S designation. So if you have I don't know, I can't think of any right now. I'll draw a Fisher projection. OH, H, CH3, Br, and then you had the mirror image of that, OH, H, CH3, Br. One of these is going to be R and one of these is going to be S, but these would have the same condensed formula, and so would these. Diastereomers. Diastereomers are anything other than enantiomers. So diastereomers can be cis-trans bonds. They could be cis-trans double bonds. They could be, if you have cis-trans on a cyclohexane ring, those would be isomers. These would all have the same condensed formula. And then they could also be if you have 2 stereocenters, and like say one's are R and the other is RS. So it's not a mirror image, but one chiral center has changed. Those are all diastereomers. So that's my isomer flow chart. And actually, I already did draw an example of all of these. So yay. To identify the chiral center in the molecule below, R or S. Okay, this is going to take a long time, but we're going to do it. Okay, so to identify the chiral center, you look at the point of direct attachment, and whichever one has the highest molecular weight is going to be the highest. There's going to be the highest priority. So this oxygen is obviously the highest. Then if we look at these 2, they're both carbons. This hydrogen is obviously going to be the lowest. These are both carbons. This carbon is attached to 2 hydrogens and an oxygen. This one is attached to 2 hydrogens and a carbon. So actually this is the next. And then you just connect 1, 2, 3. And if I connect 1, 2, and 3, it's going left at the top, so that's S. But because the hydrogen's coming towards me, I want the opposite of that. So the actual configuration for this one is R. And then if we do the bottom, this is not a chiral center because it's CH3 and 2 hydrogens. So actually, not a chiral center. Interesting. So that only has one chiral center. So I'm looking at this now. This is CH2OH. This only has one chiral center. All of these have 3. So this is a different molecule. It might be an isomer, like a constitutional isomer, but it is not going to be a diastereomer or an enantiomer. Now, if we look at this one, this is going to be the highest, and then this, because oxygen and then 2 carbons. But this carbon has an oxygen, and this carbon only has 3 hydrogens, so this one's higher. And then we'll connect them, 1, 2, 3. It's going left at the top, so that's S. And the hydrogen's coming towards, or going away from us already, so we can just say that's S. Okay, now for the bottom one, 1, 2, 3. Okay, and that's R. So now, anytime I have, oh wait, that's not R, that's R, but then the hydrogen is coming towards us, so it's actually S. So you have to be careful about that. So this is SS. Let's see. This would be 1, 2, 3. This is S, but the hydrogen is coming towards us, so it's actually R. And this is 1, 2, 3, 1, 2, 3. So it's R. So if this is SS and this is RR, and they both have an alcohol, a CH3, and a hydrogen on the top, an alcohol and a CH3, a hydrogen on the bottom, these are enantiomers. So that's those two relationship with each other. Anytime I have all of the same things attached, I'm going to be looking out for a meso compound. Like, see, these both have an alcohol on the top and bottom, a CH3 on the top and bottom, and a hydrogen on the top and bottom. But meso compounds do need to have the RS configuration because one needs to be reflecting of the other. So let's see. I have a suspicion this will be a meso compound. So 1, 2, 3. So that's R configuration, but the hydrogen's coming towards us, so it's S, and this is 1, 2, 3, 1, 2, 3. So that's S, but the hydrogen's coming towards us, so it's R. Yes, so this is SR. So I'm going to redraw this out. I'll leave the top the way it is. I'm going to try to rotate the bottom to see if I can't get it to match. So this OH is going to come here, and then the hydrogen I'm going to move over, and the CH3 to come down. Yes. So here is our plane of symmetry. So this molecule does not have an enantiomer, because if you took the mirror image of it, because of this plane of symmetry, it would be superimposable. So this is a meso compound. So it doesn't have an enantiomer. But the relationship between 1 and 3, these are diastereomers. And I'm sorry, I'm at 4 and 3. And then 4 and 2, these are also diastereomers. Now let me count up the carbons here. 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons in that one too. And 2 alcohols. So I think this is a constitutional isomer of the others. It's just that it's OH, CH2, OH, and then CH3, and the other ones have the alcohols here and here. So yeah, that should be a constitutional isomer. Okay, so this is a constitutional isomer of these 3. It has a different condensed formula than these 3. All these 3 have the same condensed formula, which would be CH3, CHOH, CHOH, CH3. And then these are enantiomers of one another. These are diastereomers of each other, and these are diastereomers of each other. So hopefully that's helpful for you and there's one meso molecule. So hopefully that's helpful for you to kind of be a general review of the bigger concepts my students wanted me to go over. If you have any questions, please feel free to reach out, and I'll do my best to help you. Good luck studying for your final.